Am I audible?
Oh, yes, ma'am.
Last session we saw nice plots, so this time we will see some problems on Bode plots. Friday we will discuss both on this week.
Okay, ma'am.
Right. So as we saw while taking an introduction about the frequency response analysis, I said frequency responses are the response to a system when the input is a sinusoidal input. So the Bode plot is the visual representation of that for a sinusoidal transfer function. So if you take a output response from a system when the input is sinusoidal, so it's the same thing, the ratio of sinusoidal output by sinusoidal, this is frequency response. Sinusoidal input, we call this as sinusoidal transfer function. So the Bode plot is the same representation where we represent the plot in two different things. One is magnitude plot, another one is phase plot. Right? So Bode is the frequency response plot of sinusoidal transfer function, where the sinusoidal input by sinusoidal output. It's a ratio of that. So it consists of two graphs. One is magnitude representation, another one is phase representation. So these two plots represent two different things. How your magnitude varies over different ranges of frequency. Similarly, how your phase of the system varies over different ranges of frequency for the given input. So the input can be constant or it can be time varying. Anything you take, but the input should be sinusoidal. Then only you will make this steady Bode analysis. Right. If I consider a transfer function like this, how do we call this? It's an open loop transfer function, right? It's like G of S in frequency domain, open loop transfer function. If I write something like this we call it as loop transfer function because it has only the transfer function in the forward path. If I write this, then it is a closed loop transfer function. We call it as M of J or sometimes T of J omega also. Both are closed loop transfer function representation in frequency domain analysis. Just a shorthand notation what we are going to see hereafter. So we will be using this. Then if only G it is open, GH it is loop transfer function. So we have seen some of the frequency response parameters like what we saw yesterday, resonant peak, what is resonant peak, and we made a comparison between time domain and frequency domain. And we have resonant frequency. Resonant peak is similar to your overshoot, peak overshoot in frequency domain. And resonant frequency is the frequency at which this resonant peak occurs. Then we saw bandwidth. So it is the minus 3 decibels. When it reaches the minus 3 decibels of magnitude, when your plot reaches that, that point is called bandwidth, and the frequency corresponding to this is the bandwidth, actually, omega b. And we also call this as cutoff frequency. In addition to this, we need to learn two other things. One is gain margin and phase margin. So you would have familiar about this before. Just want to warm up here. So we are going to use it here. So what is gain margin and what is phase margin? Can you recollect it?
Ma'am, the amount of gain that will increase before we reach the magnitude of 1, that is at minus 180 degree phase, that is gain
Hmm.
margin.
Yeah, okay, right.
And how away are
Mathematically,
we from that minus 180 degree point is
mm-hmm,
the phase margin.
right. Mathematically, it's right. Verbally, we used to say gain margin is the value of gain to be added to the system to bring the system to the verge of instability. So if you cross that particular point, then you would go into the unstable region or make the system instability. So the gain margin usually been represented using the reciprocal of magnitude of open loop transfer function at the phase crossover frequency. I can write it like this: 1 by g of j omega pc, where g of j omega is the open loop transfer function. At omega is being replaced with omega pc. This is phase crossover frequency, and it is a reciprocal 1 by. So gain margin is can be termed as reciprocal of open loop transfer function at the phase crossover frequency. This is another representation of gain margin. Similarly, phase margin can be coined as additional phase lag. Actually, how intuitively we can see that is it's an additional phase lag added to the gain crossover frequency in order to bring the system to the verge of instability. In both cases, we are finding the breakaway, or we are finding the break point where it is going to change the system from one stable region to unstable region. So gain margin is how much of gain I can add to make the system to verge of instability. Phase margin tells how much additional phase lag I can add to make the system to verge of instability. This is the intuitive uh, view behind it. But mathematically, how can we represent this is the phase margin can be obtained by adding 180-degree to the phase angle phi of the open loop transfer function at the gain crossover frequency. So how can I say it? Gain crossover GC or GJ omega GC, right? So it's an open loop transfer function. So I am going to add 180-degree to that. So overall phase margin formula would look like this. 180-degree I'm adding to the open loop transfer function at the gain crossover frequency. Instead of using g of j omega, this representation, I am just using a shorthand notation again using a pi gc, where gc is a gain crossover frequency. So the next new term here is the phase crossover and the gain crossover. So what could be gain crossover and the phase crossover frequencies? You remember?
Gain is 1 at gain crossover.
Gain is multiplied.
Gain is 1.
One. Okay, right. So the frequency at which the let me first define phase crossover because it is related to gain margin. So the frequency at which the phase of the open loop transfer function we are considering right now is 180-degree. That frequency is called as phase crossover frequency. So whenever your open loop transfer function g of j omega's frequency omega, this particular frequency omega is equal to 180-degree, then we call this as a phase crossover frequency, right? Omega PC, I would call, right? Whenever your phase of the open loop transfer function, let me write it here. Phase of open loop transfer function is 180-degree. Then this is phase crossover frequency. Similarly, the gain crossover frequency can be defined here. gain crossover frequency is a frequency at which the magnitude of your open loop transfer function is equal to 1, as you said. So this is called as gain crossover frequency, right? So whenever the gain is 1, that is gain of open loop transfer function is 1, it is gain crossover. Whenever the phase of open loop transfer function is 180, it is phase crossover. So this will occur at interchangeably. So when defining gain margin, you would consider phase crossover. When defining phase margin, you would consider gain crossover. Don't get confused with this. Any doubt in this?
No, ma'am.
Ah, it's like one-to-one related. Excuse me, let me take a call. Okay. Um, right. It's like one-to-one related. If I have a face like this, and this is 180, and this is the unity, let's take. So I would see this would be my gain margin. So when my plot crosses here at 180, sorry, at unity, this would be my phase margin, right? So it is one-to-one related. That's it. Okay. Definitions we have done. Now we'll start to solve problems and side by side we'll learn how to do Bode plots. So I want to start off with basic things. I will just give you one transfer function. G of s is equal to k. Can you say how the Bode plot would look like? The first step is always replacing s with g of j omega, s with j omega. So g of j omega is again k, there is no s term there. Right. Now, how the Bode plot magnitude, let's take first magnitude, how the magnitude of Bode plot will look like. So in general, Bode plot will be represented using decibels, right? In log plot. So whenever you want to do log plots and represent in decibels, you would add 20 log to that. You are just converting the normal plot to a logarithmic scale plot. So if I want to represent the magnitude of this is magnitude of k. If you want to represent it in terms of decibels, I would add 20 log to that. So I will add 20 log here also in the left hand side. So this is my magnitude plot. Now consider few values for k greater than 1, 0, k greater less than 0. How this will look like? Whenever I put k equal to 0, log 0.
For
Not
k equals 0, it will be just a 1 dB straight line.
Yeah, okay. Whenever k greater than 0, will it be positive, negative? That's enough.
Yeah, positive.
No, it won't be positive, right? It won't be just positive, right? Put k equal 20 log of 0.5. Calculate and tell me.
Yeah, -6.
So it will be positive for some value. That some value is the 1. So when k greater than or equal to 0 until 1, or I can write like this. When k is less than 1, this will be negative, I think. Yeah. When k greater than 1, this will be positive. When k is exactly equal to 1, this will be 20 log of 1?
0.
See, right. In k exactly equal to 1, so I can draw my Bode plot like this. So we'll be interested in 1 always in Bode. I'm taking this as 1. So when k equal to 1, my Bode plot will be here. When k less than 0 to 1, my Bode plot will somewhere here. When k equal to k greater than 1, I have somewhere here over this anywhere, right? Based on the k value, it will be k greater than 1. Put. Okay. So this is my Bode plot for just a gain k value. How my phase would look like? Phase of g of j omega would be 0 degree, right? There is no change in slope or we don't have any slope. So it will be 0 degree always. Right. Second transfer function g of s equal to k by s for an integrator. How can I write? It will be g of j omega equal to k by j omega. So if I want to write it in terms of magnitude 20 log in decibels, 20 log of k by j omega. So j, if I want to take it, okay. So it will be how the slope will look like for a pole, single pole at the origin. That's the integrator, right?
Minus 20 degrees slope per decade.
Yes. We are calculating minus 20. This will be 20 log of k by omega. If we take magnitude alone, so when omega equal to around some smaller value, if I consider start with, it will be 20 log 1 by point 0.5, 0.1 omega, considering omega, k will get cancelled. So this will be roughly around log 10, it is 20, right? When omega equal to exactly k, it will be 20 log of k by k 1, 0, and omega equal to 10k, if I take 20 log of 1 by 10, it is 0.1, to be minus 20. So your slope will change from 20 magnitude, I'm saying 20, 0, minus 20. So if this is 20, this is 0, this is minus 20. Your plot would look like this as the frequency changes. 0.1, 1, 10, right? So for 0.1 it is 20, for 1 it is 0, for 10 it is. So this slope corresponds to 20 decibels per decade. So we call this as decade for every 10 because of logarithm scale 10 power we are calculating. So for every 10 changes in power, we will have some slope. That slope is the minus 20. So if you calculate this in between, you will get minus 20 y by x. Okay. Good. So with this knowledge, can we say how it looked like for this transfer function? Just ks, a zero at the origin, no poles. Can we do the similar approach? Can you solve with me? Tell me what would be k omega. When k equal to put omega equal to 0.1 k, omega equal to k, and omega equal to 10k. Look for it at different intervals and you will find it. When you put omega equal to 0.1 k, it will be 20 log 0.1, 20 log 1, 20 log 1, sorry, 10. So this will be inverse of the whatever we have calculated so far, minus 20, 0, 20. So your slope would be inversed. This will go from minus 20, 0, 20 for 0.1 here, here. So your slope will be 20 decibels per decade. What if I have a transfer function k by s square? What will be my slope? For k by s, we have minus 20 decibels per decade, right? So in that case, what would be for k by s square?
minus 40.
minus 40. Because we have whatever power we have here, it will be multiplied. It's a just you can derive it and also cross check, but it will be for k by s power n, it will be minus 20 into n decibels per decade. Similarly, for g of s is equal to k into s power n, it would be 20 into n decibels per decade. If the two zeros are there in the origin, it would be 40 decibels per decade. Now, a common transfer function g of s equal to 1 by 1 plus j omega. For this, I'm sorry, I, have, I will write it in terms of s then st. Okay, for this, how it will be? 20 log g of j omega would give me 1 by 1 plus j omega t, where t is the time constant. So if I calculate the magnitude for this, I would have root of 1 plus omega square t square, and my a or magnitude, if I want to find, it would be 20 log of 1 by root of 1 plus omega square t square. This will be minus 20 log root of 1 plus omega square t square. I'm just reversing the denominator, taking the denominator to numerator. So if I approximate this around some point, for example, if I consider omega t to be very much lesser than 1, so it is negligible. You will be left with only 20 log of 1, it will be 0. If I consider omega t is very much greater than 1, the 1 will be negligible. It will be 20 log of omega t. Right? So it can be minus 20 log of omega t. Right? This is your slope or value at which the omega is there. Based on the omega, it will change. So omega equal to 1 by t. This will become log of 20 log of omega into 1 by omega. It will be 1. So again, it will be 0. So omega equal to 1 by or 10 by t, if I consider, minus 20 log of 10 minus 20. So if the omega keeps on increasing, you will get negative value. So your slope would also be decreasing. But for that, before that, unlike your common thing, it will be at 0 at some point. When it crosses this crossover frequency, it will tend to degrade at minus 20 decibels per decade. So previously we saw for the poles only integrator, and the for integrator it is minus 20, and for the uh, 0 at the origin or the derivative control we have 20 decibels per second, right? Similarly, in the interest of time, I'm giving this. If the only 0 we have in our system, k of 1 plus st, instead of k by 1 plus st, we have only k of 1 plus st, then it will be at 0, it will be, and then it starts to increase 20 decibels per decade. Until that, it will be 0 decibels per decade. Similarly, for powers, this will get multiplied 20 into n. Here it is minus 20 into n for n powers of this transfer function location. So I think we forgot to discuss about the phase. So in the magnitude we discussed, right? For only k, the phase is 0 degree. What about the phase angle for integrator? We will have 1 by j omega. It is minus 90 degree. Yeah. Similarly, this will be j omega. So phase would be 90 degree. Right? Same for this case also. Okay. So here,
Ma'am, can you please explain that phase thing once again?
okay. See, for only integrator, our transfer function will be like this, right? 1 by j omega. So if you want to take phase, that is, we have only omega. at the origin. Then it will be pointing in the real axis. So and since it is in the denominator, we are taking that above, so it is minus 90 degree.
Okay, okay. So it's just tan inverse of
Tan
imaginary
inverse
value.
of d by a. Yeah, omega,
Okay.
tan inverse of omega, whatever value you take.
Okay.
Similarly, it will be in the numerator itself, so 90 degree, not minus. Minus won't come for only zeros at the origin. So the transfer function that looks like this, the phase will be 0 at some until this point, and again it becomes 90, minus 90. So your overall phase will be minus 90 only. Here it will be phase will also be 0, and at this point phase will be 90. Your overall phase would be 90 degree. Overall phase will be minus 90 here, it is plus 90. Okay, we saw most of the common transfer function or the elements in the Bode plot. Now we'll solve one problem, and I will explain how to solve a Bode plot in step by step. G of s equal to ks square divided by 1 plus 0.2s into 1 plus 0.02s. So far, we have been doing all the things like this, right? S plus 1, S plus 2. If we have something as plus 1 and bs plus 2, what you used to write like it is s plus 1 by ab, s plus 2 by b. This is the common practice we have done so far. But in for Bode plots or any frequency response analysis, try to keep the transfer function in this manner, like 1 plus st, time constant manner itself. So it will be easy for you to calculate. That's how this problem has been written here. Okay, it is actually s plus 5. It can be written if in terms of time domain. Just a different notation to represent. So what we used to do, we will just substitute s is equal to j omega, make everything sine j omega square 1 plus zero point 0.2 into j omega 1 plus zero point 0.02 into j omega. So first thing we have done. The next thing is ultimately in our Bode plot, we won't do any curves, right? We don't know how the curves will be, but asymptotically we try to approximate it. So we will have something like this, some changes in the plot, but for from one frequency to another frequency, it will be a constant one. For example, this is one frequency, second, third, fourth, kind of some omega c1, omega c2, I would call so far. So we are trying to find the value of this and the slope of this. This is the two different attempt we are making, the magnitude at this point at this frequency and the slope until it reaches the second frequency. So for that we need some prescribed or some representative frequencies, right? So that frequencies we are taking out this. So we call this as corner frequencies. So at this point, taking this as a testing point, we are going to find what the magnitude will be at this particular frequency. By connecting all those magnitudes, we are going to draw the Bode plot. So we call this as corner frequency. The first corner frequency would be, I'm considering only poles for now. So omega C1, I'm going to take as 1 by 0.2. Corner frequencies will be in terms of transfer function, sorry, time constant, right? 1 by time constant is the frequency, so it is 1 by 0.2. So this will be 5 radians per second. First corner frequency omega c1 I call. Second corner frequency is omega c2, 1 by this one 0.02. So this will give me 50 radians per second. Okay, now we found the corner frequency. First, for simplicity, consider k equal to 1 in any function to plot the Bode. Now, the overall transfer function will be j omega square divided by 1 plus zero point 0.2 j omega into 1 plus 0.02 j omega. The step 1 is to calculate the slope. So consider these are step 0. Step 1 to calculate the slopes. So here this we are going to do first. So calculating slope at all the elements. For example, the first element is your 0, j omega square. This I am considering first, second, third. Okay, right. First is the your numerator. Second is your 1 plus 0.2 j omega. Third is 1 plus 0.2 j omega. There are many ways to plot the Bode. This is one of the method. You can follow any of the things based on the books you are following. Okay, we are going to find the corner frequency. We already found there is no corner frequency for this. For this pole, we found the corner frequency is 5. This is 50. This omega c corner frequency of 4. The next things I want to find is the slope. How to find the slope? So that's why we did the warm up session. So if it is j omega square, that's 0, it would look like this j omega. So it is ks square, j omega square. It's k j omega square. So how much would be the slope?
40.
20 into 2, that is 40, right? 40 will be the slope here. Then this is the transfer function. 1 by, for example, it's a transfer function, one denominator. So if it is 1 by, it looks like 1 by 1 plus st. It's another 1 by 1 plus st. What is the slope we found for this? Minus 20 or plus 20 it would be.
Minus 20.
So two slopes, that is minus 20, minus 20. The next thing is we are going to find the change in slope. So between one point to another point or one frequency to another point, what is the change of slope happened? I know these are all the slopes at different frequencies, but between these two, how it has been changed. So if there is no change here, so this change in slope will be 40. Between here, it has changed from 40 to minus 20. So 40 minus 20 is 20 at this point. Actually, the slope at this point will be 20 because of the change or the pole that exist here. Then from this, it would be 20 minus of minus, 20 minus 20, it will be 0. No need to change anything, just whatever sign it is there, add it together. That's it. Any doubt in this step? Change in slope step?
No, ma'am. So, ma'am, what we are doing is basically first figuring out where each component of the transfer function is going to trigger, that is the
Mm-hmm.
corner frequency. Then we are calculating the slope based off
At
of the
that
general
corner frequency.
forms we had, and
Yeah.
then we are just like subtracting or adding the slopes respectively.
Yes. And then we are going to find the magnitude at that particular corner frequency. That's it. Then if
Okay.
we connect all those dots, we will get the Bode plot.
Okay.
Okay.
So,
To
ma'am,
find the,
the
yeah,
k is not 1. So, should we shift? Should we start from some other value?
no, we are assuming k equal to 1. That's okay. You will
Okay.
get for any value it will be. We are doing approximation only, no? So it doesn't matter. It's a
Okay.
constant anyway. It doesn't change any slope or anything.
Okay.
Okay. So the next step is we found the slope. Now we are going to find the magnitude. So finding the magnitude would give me A equal to change in slope, or I can write A, okay, I will write like this, plus A plus slope into log 10 of omega C2 by omega C. So this is the common formula for this. Why we are doing this is, any idea why this formula we are using? Like common guess. So what do you want or why we are doing it? No idea. So when going from one frequency to another frequency, for example, omega C2 to omega C1 to C2, here it is 5 to 50 we are going, right? So that is similarly 1 decade we are calculating. This is 0.5 to 5. It can be written as 0.2 to 1 by 10, right? So this we are switching from switching between 1 decade. So the gain can be increased by plus 40 or plus 20 or whatever way based on the transfer function. It is zero, whether it is poles based on. So we need to know where exactly we are lying. That's why we are doing this. Step to do this is first, whatever magnitude we have calculated so far, we will take it and do it iteratively. That's what the idea behind this is. The first slope is that first we'll calculate as we do always, right? 20 log of g of j omega. So what is 20 log of g of j omega? Here is j omega what we okay. Before considering it, I want to introduce two other frequencies because this corner frequency starts at 0.5, right? So this corner frequency starts at 0.5. The next frequency it is 5. So in between this we know, but before and after this I want to know something. So I am taking one minimum corner frequency omega CL and one high corner frequency omega H, whatever CH or whatever we call. Okay. So that it will be complete. Otherwise, we will have only two plots and one slope, right? So if I want to complete and see how the asymptotic plots looks like, I am taking arbitrarily one lower point and one higher point. That's it. You can take anything. You can take 100 also, but I'm just taking 10 for now. Okay. And first, I'm going to calculate at omega equal to omega CL. Here it is 20 log of j omega square divided by 1 plus some j omega plus 1 plus some j omega. Two transfer functions I have. But denominator, it is going to be 1 because your frequency is very low, around 0.1. So I'm going to approximate this and take only the numerator, j omega square. Okay. What this will give me? 20 log of omega square, 20 log 20 log of 0.1 square, 20 log of 0.1, what it will give? 0.01. Okay, let me calculate it. 20 into log of 0.01.
Minus 40.
Minus 40. Okay, first thing I found is that minus 40 here. It's my decibel. It's in minus 40 decibels. Right. Now, the first corner frequency is at omega equal to omega C1. I am going to calculate. Same, because there is no change here before. So, I'm going to keep that as it is 20 log of omega square. Instead of omega, it's just 20 log of 0.5 square. This will give me something around 12 minus 12 decibels. The next thing is to calculate it. Omega C2, omega equal to omega C2. This will give me 20 log of 5 square. It is instead of 0.01, if I put 5, 25, I get 28 decibels. So these are all the slopes, starting point at the magnitude at the corner frequencies. Right. Now I want to see the change between these two frequencies. To find the change between these two slopes and the magnitude, we are going to use this formula. So what it will give me is slope between omega C1 to omega C2 into log of omega C2 by omega C1 plus earlier magnitude, whatever we calculated first. The first magnitude we have calculated is this 28, right? 28 plus log of 50 by 5. This would give me 48 decibels. Again, at high frequency, we have to calculate, right? Omega equal to omega h. Following the same thing, I want to find between omega c h to omega c2 into log of omega ch by omega c2 plus this frequency, the before magnitude we have calculated, old, I can say old, one from the previous steps. So that would be 48 plus, so we are adding it together. We are adding the slopes together, that's it. Divided by, what is that next frequency? Okay. This itself, it's 5 and 50, no? It's not 0.5. 5 and 50. So I'm adding 100 here, not 10. 10 would be intermediate. So it will be 100 divided by 50. It's 48 plus log of 2. What is log 2? Okay, okay. I made a mistake here. I forgot to add the slope here, right? It's 20. Because the slope here is 20. This this slope. Okay.
Ma'am, can you explain this formula again?
Yeah, 1 minute. I will write it here. So if this is my asymptotic plot, okay, we take like this is one of the frequencies omega c, omega c1, omega c2. Okay. Now I found a magnitude m1 here. For example, I am at some minus 10 decibels. Let's take. Okay. So I want to see. I have a 0 here. So my slope would be. Okay. I have a pole here. So my slope would be minus 20 decibels per decade. That I know. So if I from minus 10 I go 20 decibels per decade where I would be landing. That point I want to find. So this point I want to find. So
Okay.
that is this formula is telling us. So I am adding together everything so that we will get a continuous slope of coming from one corner frequency to another corner frequency. Just finding this steps everywhere that we are doing now.
Okay.
So this would be into this 20 slope here. We are intoing the slope, right? So that I missed here. Just add it here. And here the slope would be 0. So this will give me again 48 decibels per decade because the slope here is 0. Okay. Now what I have is at omega equal to omega L, my magnitude is minus 12 decibels here. And when omega equal to omega C1, it is 28 decibels. From omega C1 to omega C2, it has changed drastically to 48 decibels. From omega C2 to omega H, there is no change. It has stayed as at 48 decibels itself. So, if I want to plot my Bode, if I plot the Bode plot, considering this as the lowest one. So I'm taking minus 12 here and some 0 here and 28 here and 48 here. Just using whatever is there in the whatever we found. So I have started from point 1, that is very less value, and I took 5 as another frequency, 50 as one, and 100 as the another omega. So if I want to connect the dots at 0.1, it is 0.1. From here, it has straight went again to 28. From 28, again it changed to 48. From 48, it stayed as it is. So this is the overall Bode plot of my system. So for here, if you see, it would be 40 decibels per decade. This would be minus 20, sorry, was 20 decibels per decade. This is 0 decibels per decade. So that's how we calculated here 40, 20, 0. So if I connect all the slopes, my magnitudes would be this minus 12, 28, 48, and it stayed at 48. Let's say. To find, see if we start from here, I would, if I use only this two corner frequencies, I would have only this. This doesn't seem like a plot, right? It's like a line. So that's why we have taken some other lower and higher points. So if you have any doubt, I'll just do a gist. So first we will replace g of s with g of j omega. Then we will, if there is any k, we will approximate around k equal to 1. Then we will find the corner frequencies. Then we will find the slopes, change in slopes, magnitudes, and change in magnitudes. That's it. Change in magnitudes like adding along the old magnitudes. That's the only change. Then we'll be able to plot the Bode. I will give you one more examples where you can do the other way around. So this is an important question you would expect in an exam. Decibels and omega. Always be aware of the notations we use. Sometimes if you don't use units properly, you would lose mark. 60 decibels per second decades minus 40 decibels per decades. I'm not drawing according to that, just follow the math. Minus 60 decibels per decade. Just somewhere in here. They didn't mention anything about the y-axis unless one point. It starts from 54 decibels. And we are starting at 0.1 corner frequency. And the other frequencies are 2, 5, 25. That's it. Then last point was not mentioned. So out of this, I'm giving options. Try to guess the transfer function out from this. What will suit the most? And give me with reasons. Give me the answers with reasons. Can you guess the answer to all the things training we did so far? The first one. So if it has to start with minus 40 decibels per decade, what should be the reason?
Double poles at origin.
Exactly. Very good.
Either
So
A or
mine,
B.
there is no constant zero. It is not starting with 0 and minus 40. Then it is like 1 plus st the whole square kind of scenario. This is starting straightly at minus 40. So it is very evident that there are two poles at the origin. So I can rule out this easy way to rule out. So out of these two, then you see it is being added minus 20 decibels per decade. So this could be the reason of some pole acting in the direction. So one pole must be there in the, so two poles at origin we already confirmed. One again, one another pole should be there so that it will be added. Now from minus 60, it is again getting decreased. So 1 plus 20 is there. So there should be 1 0. That's why it is getting minus, so it becomes minus 40 again. Then again it gets increased. Minus 20. Got added. So again, one pole should be there. So totally two poles at origin, two poles, two another poles, and one zero. So which option would be most suitable out of this? Both are suitable based on this logic. Everything has 1 0, two poles, and two poles at origin. This also 1 0, two poles, two poles at origin. So now come to the filter point where we use the cutoff frequencies as the define. So now you look for the cutoff frequency set between 2 to zero point 0.1, it has degraded minus 40 decibels per seconds. So that is pole we fixed. Okay. Now 5 to 2, between corner frequencies 5 to 2, it has degraded minus 20. So your one of the pole should be at 2, another pole should be at 5. That is fixed. Then comes the minus 40. What it is? Again, one degradation has happened, right? Minus 20. So now how will you judge the gain value here? That's the point.
Using the K that we say.
Using the
K.
yeah, exactly. Using this extra information we will do. So how can we calculate this will be 54 equal to 20 log of your magnitude. Uh, what magnitude I can change? I can take. I can take around some. Okay, this corner magnitude omega, it's starting at 0.1, right? So omega, consider omega equal to 0.1. I'll use another. Omega equal to 0.1. So 54 equal to 20 log of, what is the value? S plus 5. Rest of the things are same. So S is 0.1 plus 5 divided by S square into 0.1 plus 2 into 0.1 plus 25, 20 log of 5.1 divided by S square into 2.1 into 25.1. Just calculate this using calculator. 5.1 divided by 2.1 into 25.1. There is another, this K we don't know, right? So I'm just adding K here. So this will give me 20 log of 9.7 K. It is equal to 54. Just take 10 power of this, take log here, 54 by 20 log of 9.7K, take e power, and if you calculate e power 9.7K equal to e power minus 54 by 20, K would be somewhere around 51. Not, this is the closest of all. So this option would be the correct, right? Okay. Similarly, expects problems for calculating. If we give a transfer function, you can be asked to find phase margins, gain margins. We will solve some problems on Friday. Phase crossover frequency, gain crossover frequency. We will give some Bode plot for that and ask you to find this. Otherwise, Bode to transfer function to Bode. So we will give one transfer function and ask you to find the proper or valid Bode for that particular transfer function. That can be a question. So these are some questions around this. Otherwise, some 1 2 marks question would come from whatever we solved. If I give a 0 s power n, how would be the, what is the slope? We can ask something like that. Just these are all testing your basics. That's it. Any doubt in today's session?
No, ma'am.
Okay. Right, we can find out.
Thank you, ma'am.
Thank you.
Ma'am, I had a doubt in the Nyquist plot.
Oh yeah, yes, ma'am.
Ma'am, I don't really understand what is the, like, if a point on the Nyquist, if the Nyquist plot is going through -1, that point, which is the point of unstability. And what does
Why?
that exactly mean?
Why you're looking exactly it's minus point one.
No, no, no. If I know that if the Nyquist plot is encircling that -1 point, then that means instability, right?
Uh-huh.
So, is there a case where the plot can like go through the -1 point somehow?
Look, you are asking for some examples where it encircles minus one, but it is unstable.
No, ma'am. I understood the encircling part, but is
Uh-huh.
there a case where the line can actually go through the -1 point?
Oh, go through the minus one point. It can be. It can be. There are cases.
So, what does that mean? What can we infer from that?
Actually, it will be. We will ignore that. We won't take that as an encirclement point. We won't generally define questions like that. I never worked out any problems, but it is possible. It's not like it's impossible, but it is counted to be not encircled. That's it.
Okay, so it does not directly infer instability or something.
Yeah, yeah. We will count that as a not encircled, and based on your open loopholes, we will comment on the stability
Okay,
for that particular transfer function.
okay, ma'am.
Mm.
That's all. Thank you.
Right. Okay.